The second problem that we're going to be looking into is this problem. If you have a linearly independent set of vectors, so they span some subspace here of Rn, can you extend it to a full basis of Rn? Can you come up with the missing vectors that would turn this into a basis of Rn? Obviously, if k is equal to n, then the problem is solved. There's nothing to add. But if k is smaller than n, then you have a number of vectors you could add. What's a reasonable way to go find these missing vectors? When we talk about orthogonality, one of the things we'll see is that a potential answer for this question is to find a basis of the orthogonal space to the subspace spanned by the vectors u1 to uk, but we don't have enough machinery to allow us to do this efficiently. So what's the thing? We can still use the row space algorithm, in fact, to try to come up with such a basis. So the way it works, you'll build an n by n matrix A, and the first k rows, and the rows here, will be the vectors u1 to uk, the ones that you actually know as being part of your set of that is linearly independent. The remaining n minus k vectors, they're unknown. We don't know what they are. We keep them in there as symbols. So I mean, they look the same here, u1 all the way to uk, and uk plus 1 all the way to un, but these would be actual vectors that are known, and these would just be like literally something you would write as uk plus 1 and as un. We have seen that the rows of the matrix A will form a basis of Rn if and only if the rank of A is n, which is to say that every single row has a leading one in any row echelon form of A. Now we can start the process. We can start row reducing the matrix A, but the only part that we can work on is the part that we know, like rows 1 to k. And once we do that, we see which columns the leading ones fall in. And then you will choose the remaining vectors from the standard basis of Rn, which is to say the vectors that have a 1 in a position and zeros everywhere else. You'll do that to be sure that there's a leading one in every column. Then you'll have a rank which is automatically n. So let's say we start with a linearly independent set. Well, not super surprising. Here there's only one vector, and it's not the 0 vector, so it's automatically linearly independent. It's in R3. Can we come up with a basis of R3 that contains 0, 1, 1 as a starting point? Okay, so the dimension of R3 is 3. So you'll need 2 more vectors. So how do we do this? We set up the matrix A. In the first row, U1, we have the vector that we are aware of, and then we'll be adding the symbols for the remaining 2 vectors. And then we reduce, or row reduce, the part of the matrix that we know. It's already sort of row reduced, right? I mean, it looks like this. There's one leading one here, all the 0 rows at the bottom of this thing. The first non-zero entry is a 1, and then there's nothing above it, so I don't need to worry about the leading ones being to the right, the leading ones of the rows above, and so on. So this has already been reduced. I don't need to do anything. So now I pick vectors from the standard basis so that there's a leading one in every column. So we had a leading one in the second column, so we'll need a leading one in the first column and a leading 1 in the third column. So if I use 0, 1, 1, it was U1, and then 1, 0, 0, and 0, 0, 1, and I do the reduction, I'm going to get the identity matrix, a leading 1 in every single column. How did I get the reduced matrix from here? All I really did was to swap the first line and the second line. It's not the full RREF here because there's a thing above the leading 1 which is not 0, but you don't need to go to the RREF to get the rank. You just need to go to a row echelon form. So 0, 1, 1, 1, 0, 0, and 0, 0, 1 would be a basis for the row space of A, which in this case is the same thing as R3. They're all linearly independent. If you do this after having row reduced the part that you already knew, you're guaranteed to get n vectors that are linearly independent in an n-dimensional space, and then that's automatically going to be a basis. Let's do a slightly more complicated example. Let's say that I have 1, 2, 3, 4, and 2, 4, 7, 8. These two vectors are linearly independent. When I have two vectors, it is sufficient to check to see if one is a multiple of the other. Okay, so I'm looking for a basis of R4. I will want 4 vectors in total, U1, U2, U3, U4. U1 is going to be that first vector. U2 is going to be the second vector. I place those in the first 2 rows of my matrix A, and then I have 2 more rows to fill up. Okay, so we row reduce as much as we can using the part of the matrix that we know. I'm trying to create a 0 here underneath the leading 1 for the first row. How do I do this? I want to create a 0 in the second row, so I'm going to do something times R1 plus row 2 into row 2. Remember, if we're going to be placing this into row 2 has to appear alone here. And what is it that I need? Well, I have basically A times row 1 plus row 2 into row 2, A times 1 plus 2 should give me 0. Choice A is equal to minus 2. So there's your minus 2. So that second row is going to become minus twice the first row plus the second row. If I do that, if I multiply the first row by 2, I get 2, 4, 6, 8, and I subtract that quantity from the original second row, 2, 4, 7, 8. The only place where there's a difference is right here. Okay, so by doing this, I have created a row echelon form. Not necessarily reduced, that's not important. The point is, I have a matrix here with 2 leading ones. Columns 1 and 3. So I'm picking 2 other vectors, U3 and U4, and basically what I want is a vector from the standard basis that has a 1 in the position or positions that are not columns with leading 1. So I want a vector with a 1 in the second position and a vector with a 1 in the fourth position. Well, the natural things would be these ones. Sure enough, 1, 2, 3, 4, 2, 4, 7, 8, 0, 1, 0, 0, and 0, 0, 0, 1. If I reduce this fully, I've already done that first little bit that creates these leading ones here, and I just swap the second row and the third row to get 4 leading ones. And so the rank of this matrix is 4. So the dimension of the row space is 4. So the extension, according to this row space approach, would be 1, 2, 3, 4, 2, 4, 7, 8, and I add to those 2 vectors 0, 1, 0, 0, and 0, 0, 0, 1. This is obviously not the only basis of R4 that contain these two, but it is the simplest way to extend a linearly independent set to the basis of the whole space.